Hello everyone, this is me Mohammed, and in this video I want to update the ADC single conversion mode tutorial to make some improvements and to add some more useful content. I want to split this tutorial into two parts. In the first 5 minutes I'll just show you how to implement a simple analog input reading with CubeMX and Keil microvision, and in the second part I'll do the same thing but in a very lower level programming and without the help of CubeMX. So for those of you who are interested in low level details, they will find the second part very exciting. So let's make a start. As usual, open CubeMX and click on New Project. Select the right board, STM32F4 in my case. Alright, now the first thing we need to do here is we need to select our analog input pin. We know the STM board has got 3 analog to digital converters and it has got 16 analog input channels, which mean that we can connect 16 analog devices to the STM board, but it has got only 3 analog to digital converters, so we need to select which ADC we want to use. So if you expand ADC 1, you see the same 16 channel options, similar for ADC 2 and 3. So since I only have one and only input, analog input, I will choose ADC 1 to do the conversion, and I want to select channel 0. And this turned out to be PA0. So I would need to connect my potentiometer to PA0. And by the way, my analog input is a potentiometer that I need to connect to this pin now. I would also enable the onboard LEDs, they might be useful. And from the previous videos you already know that the onboard LEDs are connected from BD12 to BD15. Before I carry on, just for the sake of clarification, I've got a potentiometer connected as my analog device, and what you need to do with the potentiometer is you need to connect one of the far end to VCC and the other end to ground. You connect the middle pin to the analog input on the STM board, which is PA0 in this case. So that's all we need to do in here. Let's go to configuration panel, click on ADC1, and these are the configuration options you have. You can change the resolution, which I really want to change. I want to change it to 8 bits. I don't need 12 bits of resolution, and data alignment, clock prescaler, scan conversion mode, and many other configuration options that you have. I'm not going to touch them now. I'll clarify them in later videos. They will come useful, for instance, the scan mode, continuous mode, and others. For now, that's all we need to do. If you don't know what 8 bits mean, just Google it. It's that simple. 8 bits is going to be the range from 0 to 255. 10 bit will be from 0 to 1023, and so on. So that's all we need to do here. Click OK and generate the code. I'll give a project a name. I'll call it ADC Single, and select the right IDE, MDK ARM v5 or Keil microvision 5, and click OK. Once this is done, click on Open Project to launch your IDE. And in here, expand this folder and expand Application User and open the main. And as you can see, this is the main generated by CubeMX. Already has got all the low-level configuration, the clock speed settings, the ADC configuration that we did graphically, but here it's done in software, and the GPIO initialization and pinouts. So that's all generated by CubeMX. Now all we need to do is start programming in here. And what I need to do is, I need to read my ADC value and wait for 100 milliseconds. I don't want to read continuously, and that's why we call it single conversion mode. And to read the ADC value, there are a few functions that we need to use, and you can find them in here under ADC driver. The first function is to start the ADC, so HAL ADC start. And this only takes one parameter, which is the ADC handle type diff, and you will see all the type diffs defined at the top by CubeMX. And here it is. It's called HADC1. Then the next function we need to use is poll for end of conversion, because this poll takes some time to get the value converted from where we started, so we need to use poll for conversion function. And this function takes 2 parameters. It takes the handle type diff again, but we need to add a timeout because it will wait for a certain time. And I just want to give it 5 milliseconds because ADC should be really quick. It should do the conversion within 11 clock cycles, which is something like 3 microseconds. Next, we need to check if the result of poll for conversion is success, then we'll carry on and get the ADC value. And that's how you check. Because ADC poll for end of conversion returns a status type diff, HAL status type diff, and HAL OK will return HAL OK when the conversion is completed and is successful. And when it is like this, then I'm going to go ahead and get the ADC value. And you get the value with a function called, very intuitively called, HAL ADC get value. I need to write it down here. This function takes one and only parameter, which is the handle type diff. I'm sure you already guessed by now. Now, I need to define an unsigned 32-bit integer for the return of this function, for the return of the getValue function. So, we get our value. If both conversion is successful, we read our ADC value. And now, one last thing we need to do is we need to stop the ADC to clear all the flags, so that when we start next time, all the flags are cleared up and we're ready to go. That's all we need to do. Let me add the 100 milliseconds delay and we should be good to go. Perfect, we're finished. Let's compile the code and upload it to the board and get into the debugging mode to read the ADC value. Okay, click this to upload to the board, and don't forget to connect your board as I just did. Obviously I need to upload again. Perfect, let's get into debug mode to read the potentiometer value. Before we run in the debug mode, we need to add the ADC value into watch memory so that we are able to watch it in real time. Right click, add ADC value to watch 1, and Bob's your uncle. So let me just remove the hexadecimal view so that I can see it in decimal display, and click run. I'll play around with my potentiometer, and there we go, it changes value, and maximum would be 255, and somewhere in the middle and back to 0. Okay, that's simply how you implement ADC single conversion mode with CubeMX. And if that's all you're looking for, you can stop and close the video here. But if you want to know more about low-level implementation and how to implement the same thing without the use of CubeMX, then carry on watching. Okay, to do the same thing without the help of CubeMX, then we've got to do everything from scratch in Keil Microvision. Click on Project, and you Microvision Project. Now select a location to store your files. I'm going to store them in here, create a new folder, I'll call it Single ADC. And so as my project. Now you need to select your board. It's ST Microelectronics F4 series 07 VG, and it's VGT, and click OK. Now you need to select the software components manually, of course. First thing you need to select is go to SimSys and enable the core software component. Then go to Device and enable the startup, and go to Framework and enable Classic Software Component. This one requires some other software components. Click on Resolve to enable them automatically, and then go to ST32F4 HAL and enable ADC Software Component, because we're going to use ADC. This one requires DMA, so resolve that, and that's all you need to do on the software components, and click OK. Now this has generated a Keil Microvision Plank project for us, as you can see here. If I go to the project window, we have a target with some driver files but without a main file, so we need to create the main ourselves. To create a main file, right click on this and add a new item to the group. It's a C file and you call it main. Now in the main file, the first thing we need to do is we need to include the HAL library driver, and it's STM32F4XX _HAL.h. Perfect. Next, we need to write our main function, int main, with the infinite while loop at the bottom. And the first thing to write in here is to call a function called HAL init to return everything to the default state. It's a good practice to call this function when you do things manually, because it will return all the peripherals registered to their default state. Next, we need to configure our analog input. We need to enable PA0 and set it as analog, and we're going to do this in a separate function. I'm going to call it void GPIO config, and void takes no parameters, and I'll define it at the bottom. Now you can see that we're doing everything ourselves. Unlike when we used CubeMX before, CubeMX was doing all the low-level functions for us, but it's quite useful to know the low-level things. So in GPIO config, we're going to discover the GPIO driver, the one that initialize and configure the pins. So on the driver there are description on how to use it. It's very well documented. The first thing we need to do is we need to enable the clock of that port using this function. So I'm going to call it first. I need to enable the clock of port A, because using PA0. So far so good. Next, we need to use HAL GPIO init. It's a function that initializes the peripheral, but this function expects the port, which is GPIO-A, and also takes a GPIO init type diff that holds all the configurations. This type diff is actually just a structure that stores the configurations. So let me just define it here. It's GPIO init type diff. You will soon get the idea. And I'll call it my ADC pin. It's just my ADC pin. And you just copy this and paste it in here, and it will act as a structure. So my ADC pin dot mode or dot pin, and I want this to be pin 0. And the same thing for mode. Mode gonna be analog. What else? I'll just double check that it's not pull up or pull down, so I'm gonna put this as no pull. Perfect, that's all I need to do. Now it's enabled and set up as analog. So I just need to implement those configuration by passing this type diff or structure to my init function. Yeah, so basically this one can enable port A and set PA0 as analog input. Next is obviously to configure the ADC device, to set the resolution, end of conversion flags, select the channel, exactly as we did in CubeMX graphically, but now we have to code all of it up ourselves. So I'm going to do this in a separate function too. I'll call it void ADC config, and function definitions go at the bottom by convention. And as we did with the GPIO driver, we're also going to do the same with ADC. We're going to open the ADC HAL driver and read the instructions. Okay, so first thing is to enable ADC clock. It's a different clock than the port. It's ADC device clock. Yep. To enable the ADC clock, and it's ADC number 1, so I need to select the number ADC 1. Perfect. Second thing we need to do is to initialize the ADC, and here are the description for it. So we need to call in HAL ADC init. This one takes another type diff similar to the GPIO type diff and implement some configuration to the ADC. And this one takes only the ADC handle type diff. And so we also need to define a handle type diff. CubeMX have defined this for us at the top, if you still remember. So I need to define it again myself. Okay, I'm going to copy it so that I can use it here. Okay, first thing we need to set up is the instance, and the instance is just ADC1, because we need to use ADC1 as our instance device. Then we're going to do some initialization. The first initialization is we're going to set the resolution to 8 bits. Perfect. Another initialization settings is going to be the end of conversion selection. I want to select this as end of single conversion. So at the end of every single conversion, the end of conversion flag will interrupt, so to speak. Then one more initialization, I believe it's the data alignment. This is very important. So I want the data to be right aligned. ADC data output register holds 16 bits. But I only have 8 bits, so I want them to be aligned to the right of that register, not towards the left. I think that's pretty much it. Next, I just need to implement those configuration by passing the handle type diff to the init function. And the next thing we need to do for ADC configuration according to ADC driver is to do the ADC config channel, is to select the channel number, channel rank, and to do things like regular group settings. This is quite important too. Okay, this function takes 2 parameters. It takes the ADC handle type diff, which is similar to this one, and channel configuration type diff, which I need to define here. I don't have to define it globally. And by the way, the reason we define this handle type diff globally is to be able to use it with the other function like HAL ADC get value, HAL ADC start and stop that we will use in the main. If we didn't define a global variable, we won't be able to access it. So that's why I defined it at the top. Now let's go back to here. It's already very long. So let me copy this and start configuring it. The channel is going to be ADC Channel 1 or Channel 0, and then the rank is going to be 1 because we only have one and only conversion, and the rank of this conversion is 1. The sampling time, this is rather important. Sampling time, I want to give it 15 cycles. According to datasheet, I think 8 cycles would be enough for this, but I'll give it 15 cycles. And that's pretty much it. So let's just copy this handle type div and paste it in here. And as a pointer, of course, so we need to add the ampersand sign. Okay, so having done the PI configuration and the ADC configuration, there's one more thing we need to do before we're able to start. We also need to enable the SysTick interrupt to be able to use the HAL delay function. In CubeMX, CubeMX does this for us, but now we have to do it manually. And this is again to be able to use HAL delay function. HAL delay uses the SysTick interrupt timer, so we have to enable it and set it up. And that's how you configure the SysTick interrupt. You set the clock source and speed with these two functions, and you set the interrupt priority and enable the interrupt with these two other functions. We also got to define the SysTick handler function. This is usually defined in the STM32F4.it.interrupt driver, but I didn't include it in here, so I've got to define it manually myself. And it's very simple: SysTick handler, and you call in HAL increment tick function. So now we're ready to start. We did TPI configuration, ADC configuration, and we enable the SysTick interrupt. Now we need to call in all of these configuration functions in our main to implement those configurations. And we need to implement the code inside the infinite while loop. I'm just going to copy this over from the CubeMX implementation. And we would just need to change the name of the handle type div, because in CubeMX it defines at HADC1, but now we renamed it as my ADC type div, so you've got to change the handle type div name. And we also got to define this, the return of the ADC get value, and that's simply it. Now we're ready to go. Let's compile the code and upload it to the board. And click this to load the code to the board. Okay, I see how this is happening. The debugger selection is wrong. The STM32F4 Discovery board has got a ST-Link debugger on board, and CubeMX was selecting that automatically, but now we have to select this manually. Go to options for target and go to debug and change this to ST-Link debugger, and go to settings, trace, set the clock core to the correct 16 MHz clock frequency, and enable trace, and click OK. And now it should load successfully to the board. Perfect. Now let's get into debug mode and test the ADC and analog input. And similar to CubeMX debugging implementation, the first thing we need to do is to add my ADC value to the watch memory to be able to see it in real time. Now I'll also remove the hexadecimal display, and now we're ready to run the code. And let me play with my potentiometer. Perfect, changing from maximum to minimum and somewhere in the middle. And you can see the maximum value is 255. If I change the resolution to 10 bits, it's going to be 1023 for instance, and so on. Alright, that's how you implement ADC single conversion mode without CubeMX at the HAL library level. It does give you much more insight at the cost of time, but it's very useful to do it this way because you'll get to appreciate what's happening behind the scenes. Okay, now I'm going to get into an even lower level. It's the register level for those people who are interested. Register programming level is, well, you don't need to use HAL libraries, so you can delete all the HAL libraries because we can access the registers directly. I did touch upon this type of level in my first video on blinking LED, but now I'm going to do it with the ADC. Okay, let me start with the TPI config function. So I'll comment out all the HAL library functions and I'll do the register level programming. I haven't got much time left, so I'm just going to copy and paste the functions and I'll explain them. So this is RCCAH1 equal to 1 will enable port A clock, and this one will set the mode to analog, and this one would remove any pull up or pull downs. Let me clarify this more in the datasheet. So when you go to datasheet, this is the DPI port register. If you set this one to 00 for for every port you have 16 pins, and PA0 is just pin 0. So for these two fields, we need to write 0, 0 to them in order to remove any pull up or pull down. And for the model register, so for the model register, PA0 is this one. So we need to set this one as 1, 1 for analog mode, as described in here. So I've written 1, 1 in here. This is just what the second function is for. And I did the OR sign so that I don't mess up the other field. If you did OR equal 3, then it will set the first bits to 1, 1 or 3, but it's not going to affect all the others. And the first one is RCC enable clock. Let me go to the RCC register and show that to you. So this is the RCC ENR register. If you write 1 to this, you will enable the clock of port A. As simple as that. And this is what I did in here. Okay, now let's rewrite the ADC config function with the register level functions. So let me comment out the HAL library functions first. I'll copy and paste the register level functions. Now let me explain them. So on here, RCC ADC1 clock enable, well, I left the same HAL library one because I couldn't bother searching this out. And then ADC basic configuration. The first one is ADC1 control register number 1. This would set the resolution to 8 bits and set channel to 0. Let's look this up. So on the datasheet control register number 1, you can set the resolution with these two fields, 24 and 25. So I set 10 because I want 8 bits of resolution. Second line is in control register number 2. And what this does is that select end of conversion flag at the end of regular channel conversion. Let me show that to you again. So end of conversion flag is bit number 10. I need to go down music. Okay, so bit 10, end of conversion selection, I selected 1 because I want it to be at the end of each conversion. This is important. Then the sample time to 15 clock cycle. That is sample time register number 2, and it sets the clock cycle to 15. Just look this up in the datasheet, it's that straightforward. And then I set the number of conversion to 1, and so on, sequencer to converter channel 0. Alright, one more thing and we're ready to go. Let me replace the main function, the infinite value things, with the register level functions. So remove those and paste the register levels. I obviously haven't written them now step by step for you, but I'll explain them to you. They're not too hard. So this one will start the ADC from control register 2. There is a bit called ADC on, and also the regular converging channel on flag. This is in control register. Let me actually go back to control register 2. It will be quite useful to understand. Okay, so you need to set this field to 1, and also this field software start to 1 as well to start the ADC. And that's what this line is for. And then you stabilize the ADC clock. So when you start the ADC, you cannot just get the value. You first need to wait for about 3 microseconds for the ADC clock to stabilize. And then you poll for the end of conversion, and this will wait about 10 milliseconds. It waits until the status register flag is triggered by end of conversion, and then it reads the ADC value from the data register of the ADC. Again, look this up in the datasheet. It's rather simple, really. And then you stop the ADC by clearing the flag on control register 2 of AD on. And then you clear all the status register flags as well, and that's our time delay again in the HAL library. Now we're ready, let's compile code and upload it to the board, and hopefully we'll get the same result as with the HAL libraries. By the way, very sorry for the noise in the recording. Suddenly, towards the end of the recording, it started to get some corrupted noise, so I'm sorry for that. Okay, so let's carry on. Now let's load the code to the board and enter debugging mode. Run the code immediately and test the potentiometer. Okay, let me play around with the potentiometer. Wow, perfect, still working, amazing. So maximum value is 255 and somewhere in the middle. That's it. Okay, and this is how to program ADC single conversion mode in the register level. A very insightful programming method, because it gives you an idea about the microprocessor architecture. And this indeed brings me to the end of my tutorial today. If you have any questions, please write them down in the comments, and if you found this tutorial helpful, don't forget to like and subscribe. Thanks very much for watching, have a nice day, bye.